Today we investigate related rates. And related rates have to do with something that things change to with respect to that's the same. There's something that things share in common. And this will bring up a great example. The area of a circle increases at a rate of 20 inches squared per minute. At what rate is the radius increasing when the radius is 5 inches? Sounds like a horrifying problem, doesn't it? Anna is nodding. She says, does not make my Wednesday, Mr. Gentz. Like, I was having a good Wednesday till you started talking, all right? And then it got bad. Well, I'm just going to draw a picture here, okay? It's a circle. I practice at home every night drawing circles, okay? And it looks like the circle is getting bigger. Are we all okay with that? Great. I want you to think of all the things that are changing in this problem. The radius is changing. The area is changing. Circumference is changing. Diameter is changing. There's a lot of things changing, right? There's one thing that's changing that nobody mentioned. Time. Nice job. There it is. Okay, now I want to be, because this is how related rates develop, because time is that kind of unifying thing that many things change with respect to. So, for example, would you agree that as the radius changes, the time is changing as well? Would you agree that as the circumference changes, the time is changing as well? As the area changes, the time changes as well. So therefore, related rates often have this: the derivative with respect to time. The derivative with respect to time. However, in many of our equations, we never have a t variable. Okay, we never have a t variable, and you're going to see how it works out. There is one formula in this problem that's going to be very important for us to write down. Anybody know what formula that is? Area of a circle. What is the area of a circle? Area is equal to pi r squared. So in the second box is where I like to write down my formula, and I also like to write down a few of my knowns and my unknowns. For example, do you know the current radius? What is it? It's 5. Do you know the rate at which the radius is changing? We're actually trying to figure that out, aren't we? It says at what rate is the radius increasing? That's what we're trying to find is r prime. So it's important for me to identify what we know and what we're trying to find out. Now I've got this thing, the area increases at a rate of 20. So I'm going to say that a prime is equal to 20. I know that. We all good? In this box, what I like to do is I like to take the derivative with respect to time. And I'm going to bring you back for just a second here so we could just remember what the heck we're doing. Derivative with respect to x of x squared plus y squared is equal to 5. What was the derivative with respect to x of x squared? What did we say? 2x. What was the derivative of y squared with respect to x? And the reason why was because we didn't have a y variable down here, right? It wasn't the derivative with respect to y. It was a derivative with respect to x. So therefore, we attached a y prime. So I want you to look at this. Do you see a t variable in this equation at all? No. So every time you take the derivative of a variable, you have to attach a prime to it, just like the y prime. So therefore, you can see why we learned implicit differentiation. So the derivative of a is going to turn out to be a prime. And the derivative of pi r squared, what do I do with the 2? Dump it in front, so I get 2 pi r. But I have to attach a r prime. Yes, derivative both sides. You good? Okay, now Alex is seeing, hey, we know we got a prime is equal to 2 pi r prime. And he's saying, well, we know that that's 20. And we know that the current radius is 5. Is that going to allow us to solve for r prime? Yeah, looked like a super complicated problem. Really, it's quite simple. We get 20 is equal to 10 pi r prime. Divide both sides by 10 pi. We get r prime is 2 over pi. Now, I'm going to attach a label, and I'm also going to write it as a decimal. Here we go, calculator. Turn on. It's okay. There you go. All right, 2 divided by pi, and I get that 0.64. Actually, let's go to 3 decimal places just so we're used to what the AP exam is going to demand of us. 0.636. You could round up. You could just cut it off after 3, though, for the AP exam. 0.636. And what's our label? What is it that we're measuring? Okay, we're measuring the radius. Is the radius going to be measured in inches squared or just inches? Inches. And because it's a rate, we have inches per minute because of time. So our answer is 2 over pi inches per minute, or 0.636 inches per minute. I'll accept either or. Again, I'm trying to give you points on the test. However, if you take something like 10 over 20 and you don't simplify that to 1/2, I will take a 1/2 point off for that. I will expect you to simplify your fractions. Okay, yes. Yeah, if I were you, I'd just try to think of this as, area is equal to pi times y squared. If you take the derivative of y squared, you would say it's 2y prime, right? Same thing. Because the variable is not, if this was an r down here, then it would just be 2 pi r. If you were taking the derivative with respect to r, then it would just be 2 pi r. But because it's due to time, we have to attach that r prime. The derivative of a is 1 times a prime. Again, you don't see the a variable down here, so you have to attach an a prime. If it was a squared, then it would be 2a prime. Better? All right, let's try a different one. Basketball is being filled with air at a rate of 1 cubic centimeter per second. At what rate is the radius increasing when the radius is 12 centimeters? Sounds like a similar problem, doesn't it? Except I've got a 3-dimensional figure here. Basketball's getting bigger. Yay! I'm trying to show this like 3-dimensional, like. I get it. I'm not gifted at that. What do you think is the formula I want to write down? Volume of a sphere. Yeah, I want the volume of a sphere. And the volume of a sphere is this one. You're going to want to make sure you have these. Is 4 over 3 pi r cubed. That's a formula you're going to want to know. If it was surface area, the surface area of a sphere is 4 pi r squared. Okay. I'm second guessing myself. I think that's right. I should probably check. All right. What's the robot's name? Siri. Alexa. Alexa, what's the volume of a sphere? She don't know. All right. So, what do we know and what don't we know that we want to know? Okay, so we don't know r prime. Okay, what do we know? What is r? All right. What else do we know? V prime. Very good. V prime is 1. Do what I want. It's free country. Derivative with respect to time of V equals 4 over 3 pi r cubed. Nope. Zach? Got it? What's the derivative of V? 1 times V prime. 4/3 pi r cubed. 4 pi r squared r prime. Yeah! Look at that derivative. That was cool, huh? The coolest. You just rolled your eyes at me. Say apologies to mathematics right now. You refuse. Oh, my goodness. All right. So now I plug in my knowns and my unknowns. What's V prime? 1 equals. So that's 144, right? 144 times 4. Is that 576? So 1 over 576 pi is equal to r prime. So r prime is 1 over 576 pi. What's our label in? Centimeters. Do you measure the radius cubed, squared, or just regular? Regular. So centimeters per second. If you like to, you could turn that into a decimal. Because we measure the radius is a 1 dimension. Area is 2 dimensions, squared. Volume is 3 dimensions, cubed. Okay? Here's what I want you to do, okay? Right here. See it? Level 1 problems. You're ready to start trying the 1 through 6. Okay? Take out a scratch sheet of paper. Start trying a couple of them. I'll do 2 cents with Gens, and maybe we'll get to one more problem. All right, example number 3. Right triangle has a base of 12 that remains constant while the height and area increase. The area is increasing at a rate of 8 centimeters squared per second. At what rate is the height increasing when the area is 64 centimeters? What should I draw? Right triangle. You hate triangles. Wow. Put the thingy. What's the thingy? The right angle marker. Okay, got it. The base is 12, right? And we have a height. Oh, man. I am showing genuine restraint at this point. Okay, what's the formula for area of a triangle? I like to write as 1/2 base times height. Now, this is the only difference with this problem. Right now we have 2 variables, don't we? And if you were to take the derivative with 2 variables, what rule would you have to use if they're multiplied together? Product. Time out. But one of them is not changing. One of them does not change. The base doesn't change, does it? And if it does not change, you can go ahead and plug it in right away. Now, I want to be clear, folks. I want you, as you look back at our first problem, we couldn't plug 5 in right away for the radius. Why? Because is the radius changing? It is. But in this situation, is the base changing? No. So all of a sudden our formula becomes area equals 6H. So what do we know and what do we not know? What is A prime? 8. What is the current area? 64. What are we trying to find? Rate of the height. So that's going to be H prime. So I have my formula, derivative with respect to time, of A equals 6H. What is the derivative of A? What's the derivative of 6H? So I have A prime is equal to 6H prime. What is A prime? 8 is equal to 6H prime. Can I solve for H prime? Yeah, 4 over 3 centimeters per second is equal to H prime. Did we ever even need the 64? We didn't even need it. Good work. You can handle all the problems 1 through 6 right now. Tomorrow we'll get you into level 2 problems where they're more challenging.